If you've ever used a drill bit that stayed sharp long after cutting through metal, or watched a punch, die, or blade take on serious stress without bending or chipping, you've already seen tool steel at work. It's one of those materials hiding in plain sight, quietly powering factories, machining shops, and even the tools in your garage. But what actually makes tool steel so incredibly tough compared to ordinary steel? The answer isn't just that it's stronger. It's the result of carefully controlled chemistry, heat treatment, and precision engineering that transform basic iron into a material capable of withstanding extreme pressure, high temperatures, and constant wear without breaking down. Today, we're diving into the science, history, and engineering behind tool steel to understand what really gives it its incredible toughness, right here on History of Simple Things. The story of tool steel goes back centuries, long before modern factories existed. Early blacksmiths discovered that adding carbon to iron made it harder, giving birth to the first simple steel tools. By the 18th and 19th centuries, crucible steel production allowed more consistent quality, making better blades, chisels, and industrial tools possible. The real breakthrough came in the late 1800s and early 1900s during the Industrial Revolution. Engineers Frederick Winslow Taylor and Monsell White developed high-speed steel, a type of tool steel that could cut metal without losing its hardness, even at high temperatures. This was revolutionary because traditional steels would soften when they got too hot during machining. Their work laid the foundation for modern tool steels used today in everything from automotive manufacturing to aerospace engineering. Tool steel isn't a single material. It's a family of highly engineered alloys designed for strength, hardness, and heat resistance. At its core, it's still iron and carbon, but what makes it special are the added elements. Different tool steels include varying amounts of chromium, vanadium, tungsten, and molybdenum. Each element plays a role. Chromium improves hardenability and corrosion resistance. Vanadium refines grain structure, making the steel tougher and more resistant to wear. Tungsten and molybdenum help the steel maintain hardness even at very high temperatures, a property known as red hardness. These elements don't just mix randomly. They form extremely hard microscopic particles called carbides. These carbides are one of the main reasons tool steel can cut, drill, and shape other materials without wearing down quickly. Even with the right ingredients, tool steel only reaches its full potential through heat treatment. This process involves carefully heating the steel to high temperatures, then rapidly cooling it in a process called quenching, usually using oil, air, or sometimes water depending on the type of steel. This rapid cooling locks the internal structure into a very hard but brittle state. To fix that, the steel is tempered, reheated to a lower temperature, and then cooled again. This step reduces brittleness while keeping most of the hardness. What's fascinating is that heat treatment changes the microscopic structure of the steel, transforming it into martensite, a highly stressed but extremely hard phase. The balance between hardness and toughness is carefully controlled depending on what the tool will be used for. Tool steel's toughness comes from a delicate balance between hardness and resistance to cracking. Hardness alone would make it brittle, like glass, but the alloying elements and heat treatment work together to prevent catastrophic failure. The carbides inside the steel act like tiny reinforcements, blocking wear and slowing down deformation. Meanwhile, the tempered martensitic structure gives it the ability to absorb impact without shattering. Another key factor is grain size. Thanks to elements like vanadium, tool steels often have extremely fine grains. Smaller grains mean more boundaries inside the material, which helps stop cracks from spreading. This is why tool steel can survive repeated impacts and high stress without falling apart. Another major reason tool steel stands out is its ability to keep performing even when temperatures rise during heavy use. When most steels get hot from friction, like a drill bit spinning against metal, they begin to soften and lose their cutting ability. Tool steel is designed specifically to resist that kind of thermal breakdown. This is especially important in high-speed machining, where constant friction can push temperatures high enough to ruin ordinary steel tools in seconds. Certain tool steels, like high-speed steel, contain elements that form stable compounds which slow down structural changes at elevated temperatures. Instead of quickly losing hardness, the material retains enough strength to keep cutting efficiently, even under sustained heat and friction. Tool steel is everywhere once you start looking for it. It's used in drill bits, cutting blades, stamping dies, injection molds, and even industrial knives that slice through sheet metal. In manufacturing, it's essential for making parts with extreme precision because it doesn't wear down quickly under constant use. There are also different grades of tool steel designed for specific conditions. For example, hot work tool steels are used in environments with extreme heat, like forging presses, while cold work tool steels are used for cutting and shaping materials at room temperature. Without tool steel, modern mass production would be far slower, less precise, and far more expensive. Tool steel isn't just strong steel. It's a carefully engineered material designed to survive punishment that would destroy most metals. Its toughness comes from a combination of alloying elements, microscopic carbide structures, and precisely controlled heat treatment. What makes it truly remarkable is the balance. It's hard enough to cut through other materials, yet tough enough not to shatter under pressure. That combination is what makes tool steel one of the most important materials in modern industry. So the next time a drill slices through metal or a machine part lasts longer than expected, there's a good chance tool steel is quietly doing its job in the background, holding everything together. Thank you for watching. If you have suggestions for our next video, feel free to share them in the comments below. We'll be sure to give you an acknowledgement for your contribution. Thank you for joining us on this journey through the history of simple things. Don't forget to like, subscribe, and stay tuned for more stories woven through the smallest details.